AI image and video models are hitting a weird inflection point. More denoising, more compute, and even clever sparsity tricks can still make outputs worse if the model loses the right internal signals. One paper shows that motion is actually present almost immediately in video diffusion, then gets blurred away. Another shows the fastest path for diffusion transformers is sparsifying activations, not weights. And a third rethinks the residual stream itself so these models can train faster and route information more cleanly. The common thread is simple. Efficiency is no longer just about speed, it's about preserving the signal that makes generations look real. Let's explore the first paper. Physics in 2 steps. Locking motion priors before visual refinement erases them. This paper from Yonsei University and NVIDIA introduces phase lock, a training-free image-to-video framework that argues physical motion is already present after just 2 denoising steps and is then progressively erased by visual refinement. Using Cog Video X, 5B, and WAN 2.1, the authors show that a 2-step output can score better on physics than a 5-0-step output, while spectral analysis reveals an approximately 18% drop in low-frequency phase coherence from step 2 to step 50, even though magnitude stays nearly stable. Phase lock extracts a motion prior from the 2-step latent and re-injects it during full 5-0 step generation through latent delta guidance, a spatial domain constraint on interframe latent differences that avoids explicit FFT surgery. On the physics IQ benchmark, phase lock improves base models by an average of 6.2 points, raising Cog Video X 5B from 30.8 to 36, LTX Video from 26.4 to 32, and WAN 2.1 from 20.9 to 28.7, while preserving visual quality on VBench and adding only 1.06 times time and 1.02 times memory overhead. The method also outperforms direct frequency manipulation baselines, including low-frequency phase injection and full-phase substitution, which collapse the scores near 14, and it matches WM Reward's physics alignment with far less cost than WM Reward's roughly 5 times inference time overhead. Overall, the paper's key claim is that physics-aware generation should preserve early motion priors rather than prolonged denoising, because the extra steps improve photorealism while systematically eroding phase-coded dynamics. Let's explore the second paper, RT links, putting the gem sparsity in a right way for diffusion models. RT links, from Alibaba Group researchers, argues that diffusion transformers should be sparsified in activations rather than weights. Across Quen image, Flux, 1dev, and Z image, token-wise activations are intrinsically sparse, with only about 5% to 10% of neurons active, while weight sparsification under the 2 to 4 pattern destroys generation quality. The method applies online NM sparsification to intermediate activations, rescales them with norm compensation, and restores residual detail through a lightweight LoRa branch with rank 64. For single-stream models, it also skips the most sensitive mixed layers. On Quen image, RT-Links reaches FID 21.25 and image reward 1.304 on MJHQ30K, improving over the dense baseline FID 21.98 and outperforming prior weight sparsification methods such as Wanda, RIA, BAWA, and SLIM. It also stays strong on SDCI with FID 25.78 and image reward 1.226, while the raw sparse weight baseline collapses to FID 66.91. System-wise, a fused CUDA pipeline for online activation sparsification and sparse tensor core execution reduces sparse overhead to as low as 2.28% on H20 and delivers up to 1.88 times speedup in linear layers and about 1.2 times end-to-end acceleration, cutting Quen image generation time from 0.75s to 0.62s without noticeable quality loss. Let's explore the third paper, Rethinking Cross-Layer Information Routing in Diffusion Transformers. This paper from Alibaba Group, Nanjing University, Zhejiang University, and City University of Hong Kong argues that diffusion transformers inherit a suboptimal residual pathway from standard transformers, then diagnoses 3 depth-wise failure modes: monotonic hidden state magnitude inflation, sharp backward gradient decay, and blockwise redundancy. On CITXL, 2 trained on ImageNet 1K at 256 times 256, the authors replace residual addition with diffusion adaptive routing, or DAR, a learnable, time-step adaptive, non-incremental softmax aggregation over historical sublayer outputs. DAR's routing weights are conditioned either statically, dynamically, through the current hidden state, or with explicit time step injection. The time step aware variants are crucial because the denoising time signal is linearly decodable from router inputs, with test R 2 above 0.95 inches early blocks and near 1 deeper in the stack. Empirically, DAR reaches 7.56 FID on ImageNet without guidance and 2.05 FID with classifier-free guidance, while the best reported improvement is a 2.11 FID gain over the SITXL, 2 baseline and convergence to baseline quality, and 8.75 times fewer training iterations. A chunked version with chunk size 4 gives the best trade-off, and the method composes with REPA. Adding DAR to REPA lowers FID from 9.89 to 7.09 at 100K iterations, showing that routing level and representation alignment gains are orthogonal. The paper also reports that a fused Triton implementation reduces forward latency by 11.5 times and backward latency by 8.5 times at the SITXL2 working point. That's a wrap on today's AI paper highlights. Thanks for watching.